All right, so let's go ahead and learn a little bit about the general atmospheric circulation patterns. And let's start by looking at this animation. So let's set up the idealized Hadley cell circulation. What we see here is that as this Earth of ours heats up excessively around the equator due to more direct radiation, heating up this rock that we live on, it heats the air that it comes into contact with, making it unstable and less dense. And so this air rises, adiabatically cools, migrates north and south, and because it's more dense now, it sinks. Right? This is called adiabatic heating. This is creating our subtropical high pressure zones. Now that collision leads to divergence on the Earth's surface and creates our westerly winds. So our winds that move from west to east. Now at the high latitudes, due to diffuse radiation, right, we have a deficit of energy, and these thermally driven polar easterlies are created, these high pressure systems that migrate toward the equator, and in that path they collide with the westerly winds. So this dynamic collision generates uplift again, and we have adiabatic cooling. So as we study adiabatic cooling and heating, I want to focus on these Hadley cells that are roughly around the equator, symmetrical to the equator during the equinoxes, but they do migrate to the north and to the south during the different heatings of the Earth. So here we see in January, when we know that the southern hemisphere is in its summer, we see that intertropical convergent zone that we were just studying migrates southward. And when the heating of the Earth migrates into the northern hemisphere, we see the intertropical convergent zone also migrates north. So let's look a little closer at adiabatic heating and cooling with our board. Oops. Let's see if I can pull that up. Here we go. So I open up our digital whiteboard, and I'm going to create a new file, which I don't know why it's not letting me. Oh, there we go. Pull that up. We have a new file which disregards this other one. Yes, we still want to lose that one. So let's think together about an air parcel that's warm around the equator. Right? And so we see this warmer air parcel is less dense. Why is it not writing? Okay, less dense, and so it rises. And so as it rises, what's interesting to think about is that the pressures decrease as we get higher and higher into the atmosphere. Because what's holding these gas molecules to our planet loosely is the force of gravity. Right? So as this air parcel rises, what is its pressure experience? Is it increasing or decreasing? Sure enough, the pressures are decreasing the higher we go into the atmosphere. What will that do to the volume of this air parcel? Well, with less pressure on it, it's going to expand. So this air parcel that had a much smaller volume here now has had its volume increase. Well, now those gas molecules in that air parcel are going to, go ahead and cool. So we see that temperatures will decrease as this air parcel rises. And this is what we saw happening roughly around 10 north to 10 south, symmetrical of the equator around the equinoxes, but migrating to the north and south. This is called the intertropical convergent zone because these air parcels will eventually collide and rise again and cool. So let's think about what happens as this air parcel that's cool becomes more dense and migrates to the north and to the south. So erase some of this. Large eraser. And let's think about what happens in this case. Well, now we know this large, cold air parcel migrates to the north and to the south. I don't know why this is so difficult. And as it migrates to the north or the south, it starts to sink. Right? So in this zone, it could have adiabatically cooled, so much so that it actually condensed and led to rain, creating our rainforest. So we should associate the ITCZ with clouds and rain. But now this air parcel, as it's migrated toward the north and south, is more dense, and so it's going to sink. And as it sinks, what did we learn about pressures? The closer you are to the surface, pressures are greater. And so as the pressures increase, the volume decreases. And we see these air parcels now have less space and interact, and the temperatures warm up. So as we look at our Earth from 20 to about 35 degrees north and south of the equator, we have adiabatic heating, and this is called our sub to the tropics. So subtropical sinking air is moving into high pressures. So these are high subtropical high pressure zones, and what's exciting about this is that it is actually our world's largest deserts. So that when we look at a map of the Earth, we can see, wow, this is actually quite amazing. Let me see if I can find our insolation map on here. I think I have it in another one. So I think it's in this one. Right, if we look at an insolation map of the Earth, it's pretty exciting to see, wow, look at that. Intercepted solar radiation on our planet, you can see, dominates at the 20 to 35 degrees north and south. So we see by far the greatest amount of intercepted radiation on our planet is between 20 and 35 degrees north and south. Right? And these are the world's largest deserts. You see North Africa, Saudi Arabia, right? And even parts of Los Angeles and Chihuahua, Mexico, right? And this is the same in our southern hemisphere, between 20 and 35 degrees north and south. So this sinking air, adiabatically heating, is creating our world's largest deserts. And we see that happening in both the north and the southern hemispheres. Much more extreme in the northern hemisphere because we have more land mass. And just as importantly, you see our rainforest, our tropical rainforest, where we have high moisture, is where we see air is rising all year long and adiabatically cooling. So we see our Hadley cells, if you imagine this in 3 dimensions, we see air rising at the equator and sinking between 20 and 35 degrees north and south. So where we have our greatest amounts of insolation is not at the equator, but a little bit to the north and a little bit to the south, because all year long there's no cloud cover, more intercepted solar radiation can occur at the Earth's surface. So that concludes. Let's try a little quiz question about this topic, and we can do that by now pondering. Let me see if I can get this board up here to try to get them to duplicate one another. Oops. So I don't know why it won't let me do that. Duplicate. Well, let me see. I'll close this one down. Oops, that's why. So here we see, if we get back to our board that we had before and we ponder this a little bit more, we can see that it makes sense that we would have our world's largest deserts, roughly between 20 and 35 degrees north and south on the equator. So let's try to think of a good quiz question to make sure we understand what's going on. Right? So let's see. It's one that I've seen commonly is, this may not be the best whiteboard program, but I'll research better ones too. Right, so let's say that we're studying the Earth and we find that in this area that you have an ascending air parcel. Ascending means to rise, right? Would you expect temperatures to increase, decrease, or stay the same as an air parcel rises? Well, what we just learned a minute ago was that as an air parcel rises, its volume expands due to that lower pressure. That pressure decrease leads to a volume increase, making temperatures decrease. All right, that's enough for adiabatic heating and cooling. And we can stop this video. I have to figure out how. Oh, there we go. Got